Our planet's coastlines might seem permanent, like they've always been there, but they're actually in a constant, slow-motion dance with the sea. This relationship has shaped our world for millennia, and frankly, it's posing some really critical questions for our future.
So when we talk about sea level change, most of us picture one simple thing, the water getting higher, right? But that's only half the story. The real and much more interesting question is this: is the ocean itself actually rising, or is the very land beneath our feet moving? Well, here's the twist. It's both. To get our heads around how both can be true at the same time, we've got to look at two major processes. They sound a bit technical, but they have different causes, and together, they're the architects of our coastlines.
Okay, so on one side you have what's called eustatic change. This is the big picture, global one. It affects the total volume of water in all the oceans. The easiest way to think about it is like adding more water to a bathtub. The level just rises everywhere, simple as that. But then you've got isostatic change. This one's local. It's all about the land itself moving up or down. So in this case, the amount of water in the tub stays the same, but the bathtub itself is actually tilting.
So what's driving these global eustatic changes? Well, it really boils down to two huge factors. First, ice. During ice ages, unbelievable amounts of water get locked up in massive ice sheets, and that makes sea levels drop. When that ice melts, all that water flows back into the ocean and, you guessed it, the level rises. The second factor, and this one is absolutely crucial today, is thermal expansion. It's just simple physics. As water gets warmer, it expands and takes up more space.
Now for the local stuff, the isostatic changes. And this is where it gets really interesting. Just imagine the colossal weight of a 2-mile-thick ice sheet pressing down on the land. When that ice finally melts, the land starts to slowly rebound, lifting back up over thousands of years. This is literally happening right now in places like Scotland. But here's the catch. It creates a kind of seesaw effect. As Scotland rises, other areas, like Norfolk down in England, are gradually sinking. For people living there, it feels like the sea is rising even faster.
All this history, this long story of rising and falling seas, it hasn't just vanished. It's left behind some pretty dramatic evidence. You could call them geological fingerprints that tell the tale. And if we learn how to read these clues, we can really understand the forces that are shaping our coastlines today.
First up, let's look at what happens when the land rises faster than the sea. This creates something called an emergent coastline, where features that were once deep underwater are now left exposed, high and dry.
And these coastlines leave behind some amazing clues. I mean, you can literally go and walk on raised beaches, old shorelines that are now sitting meters above where the waves break today. You might also spot these incredible fossil cliffs, which were once battered by the sea but are now stranded miles inland. The west coast of Scotland is a classic place to see this, and it's a direct result of that post-glacial rebound we were just talking about. Of course, the opposite scenario is just as dramatic, if not more so. When the sea rises and floods the land, it creates what we call submergent coastlines, totally transforming the landscape into these intricate networks of inlets and bays.
This process creates some of the most stunning coastlines on Earth. You get rias, which are these beautiful drowned river valleys that form branching inlets. And then, of course, there are the world-famous fjords, those incredibly deep, steep-sided valleys that were carved out by glaciers and then flooded by the sea when the Ice Age ended. These dramatic fingerprints really show just how powerful rising seas have been in sculpting our world.
Okay, so this brings us from the deep geological past right up to the urgent present. Because while these processes have been happening for eons, today's sea level rise, it's different. It's happening a lot faster, and it's being driven by a new force.
Let's connect the dots here. The primary driver today is global warming. This is hitting the accelerator on our two big eustatic factors. It's speeding up the melt of ice sheets, and it's causing the thermal expansion of the oceans. The end result is a global sea level rise that's happening much, much faster than in the recent geological past. And that directly increases the risk of flooding and erosion for coastal communities all around the world.
Today's sea level rise really isn't a mystery. It's a direct consequence of these two powerful mechanisms working together. The melting of land-based ice, plus the physical expansion of warmer ocean water, those are the main contributors to the higher sea levels we're measuring right now.
And look, this isn't some abstract, far-off problem. It's a real and present threat to millions of people. In a place like the Nile Delta, you have a perfect storm. The global sea level is rising, while the land itself is sinking. It's that dangerous combination of eustatic and isostatic change. The Guinea coastline, even coastal California, they all face their own unique combinations of these heightened risks.
So, all this brings us to the most important question of all: what on earth can we do about it? Understanding all this science isn't just an academic exercise. It's the foundation for how we plan, how we adapt, and how we build resilience for the future.
This is where it all comes together. That amazing story of Earth's past coastlines, the raised beaches and the drowned valleys, gives us the data we need to model what's coming. By combining that long-term geological knowledge with our modern climate data, we can start to make some genuinely informed decisions.
Using this science, planners and engineers can use a whole range of strategies. Sometimes, that means building hard defenses like seawalls. But in other cases, it means a managed realignment, strategically allowing some areas to return to the sea. One of the most powerful tools we have is restoring natural defenses like mangrove forests and marshes, which act as living barriers. All of these strategies depend on one thing: accurately predicting which areas are going to be most vulnerable.
So you see, our coastlines have never been static. They are living archives of our planet's history, written by ice, heat, and gravity. The story is one of constant, powerful change. And the data from the past gives us the knowledge we need to act in the present. The only question left is how we choose to write the next chapter of that story.